In this video, I want to talk a bit more about the key players as far as elements go, and that will be the carbon, nitrogen, and oxygen, and hydrogen. So these are the elements that make up most of our mass in our body. There are also present in our body things like phosphorus and sulfur and chloride, and as I talked about before in the previous video, we also have sodium, magnesium, potassium, and calcium. And there are trace amounts of things like iron, which most people know is in the blood. There's also copper and zinc and manganese and some other things, but most of what we're going to focus on are the carbon, nitrogen, oxygen, and hydrogen. So first, let's discuss hydrogen. So hydrogen, if we wanted to talk about it in a single atom elemental form, is a proton with a single electron orbiting around it, as I talked about in the previous video. However, all elements like to have their electrons paired up with something, which is why you will usually find hydrogen like this, H2, so one hydrogen atom bound to another hydrogen atom, because these electrons like to be paired up, but if you have a negative charge, that can also make the atom less stable. So most of the time, if you're just talking about elemental hydrogen, it's going to be in this H2 form. And just hydrogen by itself like this, there's not much chemistry we can really talk about. So let's add our next key player here, which was carbon. So carbon, like I said, has 2 electrons in its innermost shell, which I will not show on here because most of the time when you're talking about chemistry, you only show the outermost shell, which are called the valence electrons. And as I said with carbon, you have 4 valence electrons. So because you put them in one at a time before you start pairing them up, all 4 are unpaired. And so if you have elemental carbon, that will oftentimes be carbon in this sort of crystal form, which is how diamonds exist, and then you'd have carbon going off in each direction on these. So as you can see, carbon makes 4 bonds. That's what these 4 lone electrons like to do, because they like to pair up with the electrons on some other carbon or other element. So, for instance, you'd have this pair of electrons shared between these 2 carbons. So, like I said, carbon can also bond to other things besides carbon, obviously. If that wasn't the case, then we wouldn't be here and chemistry wouldn't be interesting. So let's bind it with our other player that we already talked about. So carbon can bond with 4 hydrogens, which would make this, and this is called methane. I'm not going to go into sort of the naming procedure, but I will point out names when I build a molecule. So then you could also have carbon bound with another carbon, each of these having 4 hydrogens. And it would look something like this. And this is, a 2 carbon chain, and this would be called ethane, and you can keep building on more and more carbons as you go. But as you can see, when you're building all these carbons and hydrogens onto each other, it can start becoming quite laborious to write it. So almost exclusively when you're looking at organic chemistry and biochemistry, you will see things written in the sort of line form. So something like this would be a carbon bound to another carbon, bound to another carbon, bound to another carbon, each with hydrogens coming off. And as you can see here and from up over here, carbon always has 4 bonds. And that's because of those 4 lone electrons. So you will never see carbon with 5 things bound to it. That there are very special circumstances, like in deep space and stuff, where that kind of thing can happen. But as far as our biochemistry, we're not going to have anything like that. So this right here, with just the shorthand, is the lazy way to draw a molecule like this, which, if you're interested in the names, this is called butane, like the stuff that you would see in your lighters. So the carbons are at these corner points and at the terminus, and the hydrogens are not on there. But since we always know that carbon is going to have 4 bonds, you can just assume that there are 3 hydrogens on this to make this carbon have 4 bonds, and 2 hydrogens on this, so that this carbon has 4 bonds. And another concept that needs to be introduced now that we're talking about 2 different types of atoms being bound together is something called electronegativity. And this is sort of the differential association of the electron pairs in this bond right here, for instance. So the electronegativity of hydrogen is equal to 2.5, whereas for carbon that comes out to this was 2.1. Carbon is 2.5. So that means that if we're thinking about electrons in our cloud form, as I talked about in the previous video, where if we have carbon bound to hydrogen, then the electron is sort of, it has a probability of being anywhere in the vicinity of both of these atoms' nuclei. But since carbon has a slightly larger electronegativity, the cloud of electrons is going to be pulled slightly in the direction of the carbon. And this is the way that you represent that with this arrow that has sort of a plus on this side. And that's helpful because the electron, which is negatively charged, is being pulled slightly in the carbon direction, you get a partial positive charge here on the hydrogen, a partial negative charge here on the carbon, the partial being represented by this delta here. And if we have carbon with 4 hydrogens, though, which if we want to draw in 3 dimensions will look like this, we use a wedge here to show that the carbon is sort of coming out of the page a little bit. Then we use these dashes here to show that the hydrogen is going into the page a little bit, so that this would be a tetrahedral shape. So you can think of it like this is a stool that has 3 legs on it, and then this other hydrogen coming off of the top. So each of these hydrogens has that partial, or that electron density being drawn in towards the carbon. So if you want to look at this molecule as a whole and say, is there any net polarity on this molecule, you would add up each of these arrows like they were vectors. And what you'll see is, if you're looking at the molecule as a whole, if we just draw it like a circle, there's no net charge, because there's an equal amount pulling in at every direction. The vectors add up to 0. So this is what's called a non-polar molecule. And this will be the case for pretty much everything that's just a hydrocarbon. And you've probably heard about hydrocarbons before when hearing about things like fuel. And that's what these are. These are hydrocarbons. They're carbon backbones with these hydrogens sticking off of them. And they are non-polar. However, they do like to stick to other hydrocarbons. So if you have a butane like this and another butane molecule, they're both together in the same, well, actually this is a pentane, isn't it? That's 1, 2, 3, 4, 5 pentane. It's a 5 carbon molecule. So this will have hydrogens coming off of it. And these hydrogens, because they have that partial positive, if you sort of get really close to it, you can differentiate a partial positive on it. Then this partial positive can actually cause a repelling. So this would also have a partial positive. Like charges, same charges, if they're positive, will repel each other. So this can actually, for a very brief amount of time, sort of push that electron density down away from the hydrogen so that it's partial negative right here. That will only last for a very transient amount of time, but it's happening constantly where these charges are pushing on each other. And this is what's called a van der Waals. I don't remember if it's an S or a Z. Anyways, van der Waals force. And that's why even if you have a bunch of hydrocarbon molecules together, like if you're in your, gas tank of your car, they do form a liquid. They aren't just completely separated, flying off in all directions like you would see in a gas. These do have some adhesion to each other, and that's from the van der Waals forces. Alright, so the next player in our drama here is oxygen, which in its valence shell has these 2 paired off electrons plus 2 of these lone electrons, which you can see up here. It has the 2 extra electrons from carbon, which had 4 in its valence shell. So this is going to have 2, 4, 5, 6 in its valence shell. And once again, just like with the hydrogen, these lone electrons want to get paired up. So usually you will see oxygen as double bound to each other. You can add these paired electrons here. So that's why it's called O2. If you see like tanks of liquid O2 like they use for fuel on the space shuttle, that's why they call it O2, because it has 2 oxygens bound together like this. And that sort of introduces this other concept that we have, which is the double bond. And sort of to back up here a little bit, to talking about our carbons, you can actually have carbons double bound to each other, and then they will only have two hydrogens, because like I said, carbon always has four bonds. So 1, 2, 3, 4. But you can have double bonds to the carbons here. And this is how oxygen exists. So now adding oxygen into our other players here, we can have carbon bound to oxygen, and this carbon will have 3 other hydrogens. And because this oxygen wants to bind something else, the first thing you can think about it binding to is a hydrogen. And when we have a bond like this, then, well, I guess I should tell you what the electronegativity of oxygen is. It's 3.5, where if you remember from the carbon is 2.5 and the hydrogen is 2.1, this is quite a bit higher than both of those. So in both cases, you're going to have the electron density pulled toward the oxygen. So the oxygen is going to have this partial negative charge on it, and this hydrogen is going to have a partial positive charge. So with oxygen, this 3.5 is one of the strongest electronegativities of any atom. So if you have oxygen involved in your molecule, you're pretty much guaranteed to have the partial negative on the oxygen. You're never going to have the carbon pulling electron density away from the oxygen. It's always going to be on the oxygen. So we can have this kind of bond here, and this group here, this OH, is what's known as an alcohol group, which is why this single carbon with hydrogens on it was called methane, but now that we have an oxygen on it, we call it methanol. So if it has this NOL, this OL suffix on it, then we know that it has this alcohol group on it. And you can put other longer chains of carbons on here, and this, like I said above, when you had the 2 carbon chain, it was called ethanol or ethane. So this is called ethanol, and that's the molecule that we usually just call alcohol when we're drinking it in our beer or liquor or whatever. We just say alcohol, but we're actually talking about ethanol. And for both of these molecules, if you want to represent it in that shorthand way, this one would just be this. And when you have an oxygen on it, you usually also represent the hydrogen attached to it. And this is what's called, this alcohol group is what's called a functional group. And you'll see why in this video, but even more so once we start getting into actual chemistry. It's called a functional group because it functions, it does things, it has chemical properties where, like I said, with these carbon chains, these are fairly stable, they're fairly inert, they don't have much chemistry going on each of these things. But because of this large difference in the electronegativity, we start having more chemical properties going on here. And this one, represented in the shorthand, is 2 carbons with this OH on it. And like I said, this has that partial negative on the oxygen, which is what drives the chemical properties of it. So in addition to a carbon, oxygen, hydrogen bond, you can also have a carbon-oxygen carbon bond, and these can split off and keep going in other chains, but we're just focused here on this carbon-oxygen carbon bond, which in this case the functional group is called an ether. So a lot of times you'll hear people talk about ether like ether is just the name of some chemical, but ether is a type of functional group, and we don't run into this as often in biochemistry, so I'm not going to go into too much detail on this particular group, but the type of group that we run into just a lot in biochemistry is what's called the carbonyl group, which is a carbon double bonded to an oxygen, and then we can have different groups coming off of here. So this in general is called the carbonyl group, and if we have the carbon bonded to two other carbons with this oxygen, then it's called a ketone. And once again, the electron density is pulled into the oxygen. And you might have heard of ketones in the context of like the ketogenic diet, and we'll definitely cover that as we get into the nutrition and metabolism and biochemistry, but it's called the ketogenic diet because you're producing molecules that have this ketone group in it. Of course, this ketone shows up in a lot of other molecules that we'll be talking about, but it's a very specific type of ketone molecule that gets produced in the ketogenic diet. So then we can also have our carbon to carbon here, but then this, instead of going to a carbon, just terminates in a hydrogen. This is another type of carbonyl. I'll write that down over here for the sort of general form of it, carbonyl. This type of carbonyl is called an aldehyde, and you've probably heard of things like formaldehyde, which is a specific type of aldehyde that is actually two hydrogens bound to this carbon with this carbon double bond oxygen. But in general, you can have this carbon and that goes off to just whatever other kinds of atoms are composing your molecule. But the actual functional group part of it is this, which is a carbon bound to a carbon double bound to oxygen, terminating at this hydrogen, so that there's no other part of the molecule going off from here like there would be in the ketone, where you can have other things coming off of these carbons. Then another type of carbonyl that we will run into is carbon double bound to the oxygen, and then down here there is an oxygen which is then bound to another carbon. So this is the functional group. These carbons can branch off and go to whatever other atoms are involved in your molecule, but this right here is the functional group, and this is called an ester. And what's interesting, or a concept that's interesting that we can talk about now, given this ester, is what's called resonance. And that is another quantum mechanical property that we find in our molecules. So I'm just going to write it in the shorthand so that that's counted as a carbon. Then we have that going there. So we still have on this oxygen our two lone pairs, or that's what they're called, these lone pairs, that they're paired up, but they're not alone, so they don't necessarily bond to something else because they're already happy to be in a pair like that. So then you can take one of these lone pairs, and that can act, since a bond is made up of two electrons, you can actually create a double bond by having these electrons move down here. But then since this carbon can only have 4 bonds to it, it's going to kick these electrons up here, and you're going to end up with, and when you're doing resonance structures, you always do this double-sided arrow. So you will end up now with a negatively charged oxygen single bound to this carbon here, with this carbon double bound, and this is positively charged, so this negative and positive cancels out, so this whole functional group taken as a single unit is neutral, just like it was here. And when you're doing resonance structures, you put it in brackets like this to show, because what this shows is that while we're representing it as these two different forms like this, it's actually more accurate to show it like this, and then there is this sort of partial bond that's sort of shared between these two things. So we can still sort of consider this form, since it has these charges on it, as not as well, not as stable, so it's not as well represented. So the partial bond here is a little bit stronger than the partial bond here, but there's still this partial bond character going on here. And what this does is, because a double bond does not allow it to rotate. So if we had just this with a carbon down here, this carbon is constantly swiveling around, so that you could also represent it like this, because it's constantly swiveling around. But if you have this double, it's swiveling around this bond, this single bond right here. Single bonds can swivel around, but if you have this double bond character, then you cannot swivel around. So you always maintain this bond angle. And that's what's important here about this partial double bond characteristic. And so those are the main sorts of bonds between carbon and oxygen. The ones we'll run into most often in biochemistry are these alcohol groups and these carbonyl groups. Actually, before I move on, there's one other carbonyl type of group that I need to talk about, which is this, but then instead of going off to a carbon like on the ester group, we have a hydrogen here. And this is what's called a carboxylic acid. And in the next video I'm going to talk a bit more about acid, but just sort of a brief spoiler. An acid is a molecule that has a hydrogen that can easily be detached from this. And the reason this can be easily detached on here, more easily on this carboxylic acid compared to this alcohol group, which it can detach, but it's a lot less likely to detach. So this is considered an acid because if you detach this oxygen, or this hydrogen rather, you get this, which has a negative charge on it. But we once again have this resonance structure. This will have 3 lone pairs on it. One of the lone pairs can come down here, which we'll cause that to go up here because we can only have 4 bonds to our carbon. So we end up with this as our resonance structure. And once again, it's sort of more accurate to represent it as something like this with a partial negative charge going through there. So this, because the negative charge isn't just stuck on a single oxygen atom, it can be shared between the two like this. It helps stabilize it, which makes this hydrogen much more likely to come off. And that will be hydrogen ion, which is one definition of what an acid is something that releases these hydrogen ions. So this resonance structure helps stabilize this negatively charged form. The whole thing will have a negative charge, which is shared between the two oxygens, where on our alcohol here, there wasn't anything that can help resonance stabilize this oxygen, which is why this hydrogen is less likely to be released. So there are situations, like if you put alcohol into a highly alkaline solution, and like I said, we'll talk about that more in the next video, you can extract these hydrogens. But for the most part, having this resonance structure to stabilize it will help this hydrogen to be released, and that's why it's called a carboxylic acid, because it's acidic. So then, to introduce our next player, we have nitrogen, which, if we look back up here, is just 1 over from carbon. So we're adding just 1 more electron to the atom. So with the carbon, we had these single electrons, but then we add 1 more, so we end up with this pair here. And in nature, you will usually find nitrogen like this, triple bound to another nitrogen, which is why we call it N2. Like if you ever see tanks of liquid nitrogen, you'll see it as liquid N2. Sometimes they'll call it LN2 as liquid nitrogen, but nitrogen is because of this very strong triple bond, is a fairly inert gas, and it composes about 70% of our atmosphere. But because it's fairly inert, we can breathe it in and breathe it back out, and it doesn't react with any of the tissue in our lungs or anything like that. So nitrogen wants to have these 3 bonds. So the first molecule we'll talk about is nitrogen bound to 3 hydrogens. And this is ammonia. And nitrogen has a fairly strong electronegativity. Remember, oxygen was 3.5, carbon was 2.5. This is in between, so it's 3.0. And so we have our electron density getting pulled in towards the hydrogen, which makes this, if you add up these as vectors, they all have a component pointing in that direction. And so the nitrogen, or the ammonia molecule, actually has a net charge going in this direction. These hydrogens making up the legs of our tripod have the partial positive on them, and the nitrogen has partial negative. And this actually reminds me I should talk about the partial the polarity of oxygen bound to two hydrogens, which is H2O, which you probably recognize as water. And this also has the electron density getting pulled towards the oxygen, which has the partial negative charge. And so this overall molecule is polar. It has a partial charge going this direction in the molecule itself, which is different from the hydrocarbons I was talking about earlier, where it's nonpolar because it has all of the vectors pointing inward, which equalizes it out, making it a nonpolar molecule. Whereas these molecules containing hydrogen are somewhat polar. I showed here that there's the electron density getting pulled from both directions toward this oxygen. So there is a partial charge on on this molecule. Same with on these carbonyls. There is a partial charge going towards the oxygen, where there's a partial positive on the carbon and a partial negative on the oxygen on all of these carbonyl type functional groups. And so that's the same with our nitrogen here. It's not as strong of a polarity, but it's still stronger, obviously, than on the carbon. And so this lone pair on the nitrogen is, and I'll go over this in more detail in the next video, but this oftentimes likes to bind with H plus ions in solution, which is the acid, meaning that since it's binding to acid, it makes this a base. So you will often see nitrogenous molecules with these hydrogens, and then this has a positive charge on it. And when it's in this form, it's ammonia, and in this form, it's ammonium. And so this makes the nitrogen quite alkaline. It's not a strong base, and I'll talk more about the strength of bases in the next video. So then the other types of bonds we can have with nitrogen is it could have a bond with one carbon like this, and it still has that lone pair, which still quite often bonds with, should be 3, giving it plus, and this is called a primary amine. It's primary because it's bound to just a single carbon, which then if we go to nitrogen bound to 2 carbons, and quite often we draw it with the hydrogen like that, this is a secondary amine, and then we can also have nitrogen bound with 3 carbons, which is called a tertiary amine. So these are the 3 types of bonds you can have between nitrogen and carbon. You will very rarely find nitrogen bound to 4 carbons, which would give it a positive charge. So we're not really going to talk about that. So another important type of nitrogen bond that we will come across is carbon bound to this nitrogen bound to another carbon, which then is double bound to an oxygen. And as you can see, just like in the case of the ester from above, this amide bond, sometimes, well, quite often in biochemistry, called a peptide bond. Just like with the ester bond, you can have these electrons move down there, giving us a resonance stabilized structure that looks like this. So this has the negative charge, this has the positive charge. So it's resonance stabilized, which once again is perhaps more accurately drawn like this, with a partial double bond between both of these, which once again makes it so that there is no rotation around this bond, so that you always end up with this same sort of bond angle like this. And this is an important sort of bond that we're going to be encountering quite often as we talk about biochemistry. So now that we've talked about the bonds of our main players here, which are the carbon, nitrogen, oxygen, and hydrogen, we will get to a few other ones that are notable for their, well, it's called the exception to the octet rule, which is that rule, that so-called rule that something like carbon wants to have 8 electrons in its valence shell, which is why it bonds to other atoms in order to get that 8 electrons in the valence shell. It's called the octet rule, and, well, there are more exceptions to the rule than there are atoms that follow the rule. However, in biochemistry, as we talk about carbon, nitrogen, oxygen, and hydrogen as our main players, the carbon, nitrogen, and oxygen do follow the octet rule. They always want to try and have 8 electrons in their outermost shell. But anything in group 3 or lower on the on the periodic table, they will not have to follow the octet rule. So one of the elements that we will encounter not obeying the octet rule is phosphorus. And phosphorus, as we will usually encounter it in biochemistry, is in this form, which you can see from the periodic table that phosphorus should have just as many valence shell electrons as nitrogen. So how nitrogen had the 5 valence shells, or the valence electrons, phosphorus, because in this same column as nitrogen, also has 5 electrons in its valence shell. So you'd think it should only be able to make 3 bonds, like the nitrogen when it was bound to the 3 hydrogens, or in tertiary amine and so forth. But we see here that we have 1, 2, 3, 4, 5 bonds. So this phosphorus is not obeying the octet rule. It has more electrons in its valence shell. And the reason for this is because, as we saw in the previous video on electron configurations, phosphorus has 1s2, 2s2, 2p6, which then that brings us over to here. So then we start with 3s2. Then it has 1, 2, 3, 3p3. So it has 1, 2, 3 of those p electrons. But starting in row 3, as we saw in the previous video, we have n equals 3, which means L can equal 0, 1, or 2, since L is always n, can only be up to n minus 1. So this can go up to 2. So we know that the 0 are the s orbitals and the 1 are the p orbitals. So this 2 are what are called d orbitals. So this has 3d, but none of its d orbitals are occupied. We don't start occupying d orbitals actually until we get to the 4th row here. So this has 0, 3d orbitals. However, these d orbitals can become occupied by bonding with other atoms. And that's how we, well, I think it's still sort of debated whether this model of using the d orbitals for the expanded valence of group 3 and beyond elements, I think that's still sort of debated, but it's a good model because it helps explain why in group 3, when we start having these d orbitals, even if they're unoccupied, that's when we also start seeing these expanded octets. So, like I said, in biochemistry, phosphorus will usually be in this form. So this is called phosphoric acid. And like I was saying before, acid is when these hydrogens can become detached. And we see that with this double bond to oxygen, that detaching it will help stabilize it. It'll be resonance stabilized. So taking one hydrogen off is fairly easy on this, and then you end up with a negative charge, and then with the H, and with the H, and this, so this one would be called H3PO4. This would be H2PO4 minus, and of course you can take off this one and this one. Each successive hydrogen is a little bit harder to take off because then you have to keep accommodating more charge, and then this resonance stabilization has to accommodate more. But you can eventually get all of the hydrogens off, and then you have this species, which is called phosphate, and we will encounter phosphate quite often in biochemistry. So it's important to know that phosphate has this expanded valence, and we will encounter sulfur in biochemistry as well. But even though sulfur can have this expanded valence, like we would see in sulfate, so this would be like this, and this is H2SO4, sometimes known as sulfuric acid, and obviously this can have both hydrogens come off as well because it's an acid, so we would end up with this. And we see here that this does have that expanded shell, the same as with the phosphorus, but we don't encounter sulfates like this as often in biochemistry. Usually when we encounter sulfurs in biochemistry, they are in a form that is obeying the octet rule. So we quite often see it when we're encountering the amino acids cysteine and methionine, which both have sulfur in the side chain of the amino acid that obeys the octet rule. So we do not see it in this form in these amino acids, for instance. So it would be, so sulfur, as you can see up here, is in the same column as water. So when it's obeying the octet rule, it will have 6 electrons. 2 of them will be these lone electrons. So in this case, we could have sulfur like this, the same as with water, which would be something like this. This is a dihydrogen sulfide, but in these so in cysteine you actually see sulfur at the terminal end of a amino acid chain, so it acts similar to the alcohol that we encountered before. And then in methionine we have something more like this, which was similar to that ether that we encountered before. So we don't see the sulfur as often in the expanded valence form like we do with the phosphorus when we're talking about biochemistry. So other atoms that we will encounter, like I said, are the sodium, potassium, magnesium, and calcium. And those, instead of making these covalent bonds, we actually see making ionic bonds. So the sodium, which, as I talked about in the previous video, is fairly stable in the positive ion form, and chloride is fairly stable in the negative ion form. So when we put this in water, it will dissolve, and we end up with sodium in the positive ion and chloride in the negative ion form. So that's what an ionic bond is. And same with things like calcium and magnesium, except here, since magnesium has that 2+ charge, so this would be a G, so we will see it as MgCl2, because this has -1 and this has +2, so you need 2 of these to stabilize it, and that will also dissolve in water, so we end up with 2Cl-. So these atoms here create ionic bonds rather than covalent bonds. So that's the form that we will encounter those. And then if we get down into these metals, we have things like Fe, which is iron, and that can come in 2 different ionic forms. So there's the iron that's +3 charged, and the iron that's +2 charged, depending on the number of electrons in its valence shell. Because iron, unlike the phosphorus, so iron is also going to be 1s2, 2s2, 2p, and then we go up here, so 2p6, and then 3s2, 3p6, so 2p6, 3s2, 3p6, and then iron is in this 4th one, so now we have 4s2 that we can put on here, 4s2, but then we see here, instead of being blank up here, this starts having electrons in the d orbital. So it's 1, 2, 3, 4, 5, 6 electrons in that d orbital. So we end up with, and since this is filling that 3d that was unfilled in the phosphorus, we actually take this number back down to 3d, and we had 6 of them. And so what you see is for quantum mechanical reasons I won't get into, when you ionize iron, because this would be iron that's in its elemental form, not the ion form. When you ionize it and you lose electrons, you actually remove these electrons first, so that you end up with the 3s, 2, 3p6, then these are gone, so 3d6. So this would be in the Fe2 plus form, losing those two 4s electrons. And then if you see here, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can have up to 10 d orbitals as maximum, but this has 6, so that's one more than half. And the iron oftentimes loses one of these d orbitals, which then gives us the 3s2, 3p6, 3d5, which this would be the iron in the 3 plus ionic form after losing one of these d orbitals and both of these s orbitals. And so we have these two stable-ish sort of possible ions. It should be Fe3 plus. So iron with these d orbitals has these two forms, and they can form different types of bonds. So we could have Fe2O3. So this, if it's by itself, has plus 3 multiplied by 2 is 6 total positive charge. And then these have minus 2 times 3, so 6 total. So that is how this iron 3 oxide, you will usually see it, since iron 3, that should be a 3 Roman numeral oxide, which is rust. So you'll see it written like this because it has the 3 to signify that it's plus 3. And you can also have this, which plus 2 and minus 2 times 1 times 1, they even out. I guess we can put minus there. So this would be iron 2 oxide. So we have two different ways, for instance, that iron can bond with oxygen. And when we have this going on, this is called oxidizing the iron, because it's named based off of what oxygen does, and oxygen does this quite well. So if we had elemental iron, then we had oxygen like this is going to come and steal electrons from the iron. So when you're stealing electrons, that's called oxidation. So this is often remembered as oil rig. Oxidation is loss. You're losing an electron. And rig, reduction, is gain. You were gaining an electron. So the iron is being oxidized, and the oxygen is being reduced. So this is the sort of reaction we will see When we start getting to hemoglobin and the way oxygen and reacts with the iron in hemoglobin and things like that, which are what are called redox reactions for reduction and oxidation. Alright, so before I end this video, I wanted to go over something that sort of sums up important message that you should take away from this video, and that is the electronegativity, which I call EN, electronegativity. So one of the things you can do, what's helpful here with the periodic table, is looking at the electronegativity trend. So as you go from left to right across this, electronegativity increases. If you remember, hydrogen was 2.1, I believe, then carbon was 2.5, nitrogen was 3.0, oxygen was 3.5. I don't remember offhand what fluorine was, but I think it might have been 4, which is the highest electronegativity. You would think because of this trend that neon would be the highest, but since neon already has a completely full valence shell, neon doesn't actually react very well with anything. It's quite inert. So we usually don't think about the electronegativity of neon, but fluorine has this extremely high electronegativity. So high, in fact, that fluorine will react with the air as soon as elemental fluorine touches the air. It'll actually completely oxidize the air, and well, it'll start on fire. It'll start the air on fire. So oxygen is the element that we encounter the most with a high sort of electronegativity. And like I said, fluorine is so electronegative that it will start air on fire. Oxygen is less electronegative, but it's still needed in fire. That's why when you have like a campfire, you need your fire to have oxygen, because that high electronegativity, that high potential to oxidize things, is what allows it to fuel the combustion of fire. And it is also that high electronegativity, that high oxidation potential, that we animals, humans, use for obtaining energy. As we will see when we get to it, the things like the Krebs cycle and oxidative phosphorylation is basically a slow, controlled explosion using oxygen as the thing driving that slow, controlled explosion in order to obtain energy from it. So the electronegativity of oxygen is quite important. Then nitrogen was slightly less electronegative, but it still creates polar molecules. And so, like I said, the takeaway is as you go across here, electronegativity increases. So these over here, as I talked about, have less electronegativity, and that's why they so readily give up their valence shell electrons in their highest shell and become these positive ions. So that's I mean, there was obviously a lot more in this video, but that's sort of a trend that I just wanted to make sure I pointed out before this video ended. So chlorine also has quite a bit of electronegativity, but another trend is that electronegativity increases as you go up the table. So that's why this is most electronegative. Your electronegativity will decrease as you go down, and it will decrease as you go to the left. So upper right, very electronegative. Bottom left, very not electronegative. And it's this idea of electronegativity and atoms pulling electron density because of their electronegativity away from other atoms that they're bonded to, that creates these functional groups and allows chemistry to happen. And yeah, so if you understand that, then a lot of biochemistry and a lot of nutrition and metabolism will make a lot more sense. And I will see you in the next video.